AP Stats, what is up today? I hope you're having a great night tonight as we get started with our study session on Chapter 9. This is a big one. It's a big test today. I have complete confidence in us as a team and a group, and no doubt we're going to dominate this. Just as a heads up, make sure the FRQs, multiple choice, the one that say actual on them, those are the ones we need to make sure we do. So, hey, check those out. Get those squared away there. And, yeah, we'll get it rolling on that, all right? I'm going to actually pull this up for me. We're going to look at a couple of things here. I'm an Ed Sheeran fan, by the way. Just things that you know about me, just some different things. I don't know, I just like their stuff there. I'm an Ed Sheeran fan, by the way. And it's coming through. There we are. Perfect. Boom. All right. Hey, hope you're having a fantastic day. We're going to go ahead right straight into some of these questions and get into some of the Q&A portion of our stuff today. So let's go here. We watch the sunset over the. Yeah, I just love singing. Am I good? I've never said I was good, but hey, we'll do with what we got there. Okay. All righty. Get the trumpets out. Here we go. Hope you're ready to go today. We're going to start with this term robust. What does it mean? Okay. So I thought this was pretty good. So robust statistics are any statistics that yield good performance when data is drawn from a wide range of probability distributions. This is the key, they are largely unaffected by outliers or small departures from the model in a given data set. In other words, a robust statistic is resistant to errors in the results. You're going to see this a lot in T procedures, especially, largely because as you look at this, and this is kind of what I'll highlight, you could kind of read this too. But what this means is within the confidence interval for a population mean, we're looking in terms of the use of this T procedure. We're working with an SRS. That's one of our conditions that we check. We also need to make sure that the population's approximately normal. But when we use this real life wise, there are very few populations that are approximately normally distributed. So the question is how robust is our T interval? Meaning, when we look at this data, is it resistant to errors in the results? So when we're really looking at this, the fact is that the simple random sample, that condition of having a simple random sample, is more important than it coming from a normal distribution from our population. That is why we go to the second condition, the central limit theorem, where the larger the sample size, the more approximately normal it will be. And so when we look at this, that's what we're focused on. That's the term of robust is resistant to errors or outliers. And in turn, we're really focused on that simple random sample, knowing that our population distribution, if it is not approximately normal, a lot of times it won't be, then we can go to our second condition and be able to go ahead and say, okay, it's normal, approximately normal. And as long as it's a simple random sample, to be able to use our results to our population that we're finding, we're going to be okay with that. So I hope that makes a little bit more sense on robustness, and maybe it will help more if you've got a problem that we can go over together, that we can do moving forward, all right? So with that being said, let's take out our, we're going to go to this concept list, but I promised everyone to go ahead and start on a mean world FRQ, and I'm going to make this just a little bit different. I'm going to put some new tweaks into this. This is not one of the FRQs, but hopefully I hope this helps as we approach this here, okay? So get out your calculators, get out your pens, pencils, and yeah, let's get this show on the road. Okay, so when we're looking at this idea of a t-distribution. T-distributions relate to the mean world. And I don't know if we hit that as hard as the proportion world. I know we haven't tested over it. So it's important for you to really, really get and understand where we're headed with the four-step process here, okay? So let's pretend that when the manufacturing process, kind of highlight here, is working, never-ready batteries have lifetimes that follow a slightly right-skewed distribution with a mu of 7 hours. A quality control supervisor selects a random sample of N batteries. Now, for the sake of this, we need the sample size. So let's say that he selects 40, where the mean life in that instance will be, let's keep reading. She's convinced that the mean lifetime of all batteries produced is less than 7. So let's say that our X bar was 6.8, okay? And what we'll say is that our S of X is standard deviation of this would be, we'll say 0.75, okay? I'll make it sure, actually 0.075. I'm trying to make this to where it makes sense. Make this S of X is 0.08. I like that. Okay. So the question is this statistically significant? So let's follow our process and go into the state part. So here's our state. Couple things with the state. We have the null, and some of you say it differently here, and that's fine. We have mu is equal to 7. Okay, that is the claim. And what they're saying is that the person that's kind of bringing up this lawsuit says that it's actually less than 7, where mu represents the true mean lifetime of the battery. Okay. Again, it's important to put this context in here for the state part. The alpha level, 0.05 significance level, our X bar is stated. Sometimes you actually have to find the average, but it's 6.8 with our S of X being equal to 0.08. If you want to put the sample size, you could do that as well, okay? So we've got all of these things here. We now go into part 2, which is our plan phase. We first state what type of test it is. Well, with it being mean world, we say it's the one sample t-test. Okay, we're going to kind of come off this with the calculator here in a second. Then in this part, we're going to go into the 3 conditions. Number 1, is it an SRS? Well, it is. It's stated that it was an SRS, or simple random sample. So that would be condition 1. Needs to make sure that it's a random sample, and that's the most important thing when we talk about something that is robust, that's resistant to outliers or resistant to skewed data, right? We need to have an SRS. That's important. Condition 2 is the 10%. So we'll do our 10% here. And I like to put this in to where it's 40. It's less than or equal to 1/10 of all batteries. And obviously that is true. So that condition's met. And again, this allows us to overcome independence and allows us to overcome that there. So when something's not independent, meaning when I select a battery, you obviously know that, you know, there is a small change, but it's so small based on the 10% condition, we can say that it overcomes the independence there. The third condition goes into, is the population, these are the 3 conditions, by the way, okay? Is the population distribution normal? Well, remember, something that is robust is something that resistant to outliers or extreme values, right? Well, when we look at this, this is actually skewed to the right. So we actually have to cancel this. And we go to condition 2. Remember, it only needs to meet 1. The second condition is the central limit theorem, which says, if I can talk, n is greater than or equal to 30. And in this case, we know that actually 40 is greater than or equal to 30. So based on that, we are Gucci. We found it. We don't even have to go to condition 3. We don't have to say that it's approximately normal with Now, no major skewness or outliers, because once one is met, we're good. We can go on to the next one. Okay. All right. Part three. Part three is now the do phase. I always start by drawing the picture. Or if you text, pick. Okay. Now, with this is a T distribution with our degrees of freedom that go inside of the parentheses, where this would be n minus 1. So really what this is 40 minus 1, which would be 39. So this would be a degrees of freedom of 39 that's here. With the center being at 7, and our 6.8, which is to the left side, that would be what our mean is. So if we're looking at this based off the alternative, this would be shaded to the left at 6.8. Now, again, in finding this, we know that mu of x bar is equal to mu, which in this case is always linked to what I say up here, which is 7. Sigma of x bar is equal to s of x over square root of n, which would mean that this would be 0.08 divided by the square root of 40. Okay. So let's see what we get here. 0.08. I might change the, let me see here. I'll see what I got. Let me try something. Because I did make up this problem. I wanted to make it to where it was a little bit closer. So you could kind of see the part here. Let me see something. All right, let's do this. And instead of making s of x 0.08, and again, I'm going this on the fly here, just to make it maybe a little more realistic. Let's make this 0.05, okay? Oh, I'm sorry, not 0.05, 0.5. Okay, 0.5. So just as a change here, I want you to change the s of x right here to 0.5, and basically this just allows me, and again, because I made this up as we're looking at it in this context, this would be 0.079, okay? And that's the standard deviation. So right now I've got 3 parts that have been graded, 1, 2, and 3. The key though is finding what is this p-value. Notice I am not highlighting both because it's not equal to, it's just simply less than. So to find this value, let me say a couple things on this. First off, because we're using s of x here, we do not know what the true sigma is, okay? We just don't know. So because we don't know what the true sigma is, we just know s of x of the population, we don't know it, we know just the sample, we're estimating using a t distribution. So it's important for you to understand that's why we're doing a t distribution. Might be a part of a multiple choice tomorrow, based off of the fact that we're using s of x instead of sigma, the population standard deviation. So to find this, what we're going to do is we're going to use our TCDF, lower, comma, upper, comma, mean of x bar. I'm going to put it down below. I ran out of room. Won't let me go further. And then sigma of x bar. Okay. Oh, I'm sorry. Hold up. Dadgummit. Sorry about that. That's normal distribution. And if you tried to put that in, it would say error. It's lower, upper, and then degrees of freedom as I wrap up those 3 things. I was thinking normal distribution. So with this, we only can put 3 things in. Here's the important thing. When I look at this right here, I can't actually plug in 6.8. So what I can't do is say negative 99999 to 6.8, comma 39 as my degrees of freedom. Now, most everything that I said was correct there. The only difference on this is that we have to actually use the t score for 6.8 and not 6.8 itself. So TCDF cannot, it doesn't factor in the standard deviation or the mean. So instead, we've got to, for our upper in this case, have to find what a t-score is. So that's where I have to find t is equal to x bar minus mu divided by S of X over square root of N. So this would actually be 6.8 minus 7 divided by, and we already found this, so we could just plug this in, 0.079. So let's just kind of plug this in, see what our t-score would be. So negative 0.02 divided by 0.079, and we get negative 2 or negative 0.2631. Okay, negative 0.2631, and I want to make sure that that's right. Let's see. I think I actually, let me replug that. And I think I put an extra 0 in. Try that again. I'm sorry, negative 2.63. So I moved the decimal over. So negative 2.63. Okay. All right. So what this means is that this is negative 2.631 standard deviations to the left of my mean. So 6.8 is the value. The t-score is negative 2.631. Okay. So you say, Coach, what does that mean? Well, let's go ahead to TCDF real quick. And when I put in TCDF, I'm going to put down below, and I apologize for the lack of room, but this would be TCDF lower, negative 99999, comma, negative 2.631. Again, important to use that t-score here, not 6.8, and then comma 39. Again, this is only for TCDF, not for normal CDF. Normal CDF, it's smart enough to get it there. We just don't know the, we can't factor in the standard deviation or the mean, and that's why we've got to do this here. So we got negative 99999, comma, negative 2.631, comma, 39. Okay. And what we get here is a p-value of 0.0061. Okay. So what we have here is we have a value that is less than our alpha level. So what I'm going to do is I'm just going to move this over because just want to make sure that you can see this. This was one of the more confusing parts that some people were just kind of confused on. So in the conclusion, let's just conclude this real quick. In conclusion, and I'll just put here, when we see that our p value, which in this case is 0.006, is less than my p value, we have convincing evidence to reject the everybody null. And if you said anything else, shame on you. So if we reject the null, right, we can do one of two things. We either fail to reject, we don't have convincing evidence, or in this case, we reject the null. Therefore, if I reject this, that is the only case that I can accept it. So reject the null and state that we have reason to believe the batteries perform less than 7 hours. Okay. So again, what did we do? We rejected the null because it was less than our actual alpha level. Oh, less than my p-value. It should be my alpha level. It's my fault. Less than my alpha level, which was 0.05. That's why it's important to go back through and double check it. So when we see that our p-value is less than my alpha level, we have convincing evidence to reject the null and state that we have reason to believe that batteries perform less than 7 hours. So remember, if I reject the null, the only time I can accept the alternative is when I reject the null. And that's really what I did in green here, is that's just the context of what the alternative would be there. Okay. All of them. I hope that helped you. Let me see if you all have any questions, because I know that was kind of crazy, I know. Pull this up. What's up, Lindsay? Eric? Yep, we go right straight into the voice there. T statistic, we hopped in on that. Emily, great question. S of X is normally going to be given to us. And we can look at the second FRQ in a second, Ryan. If for some reason they don't, let me show you something real quick. This might be helpful for you. Let's see here. Dun dun. Dun 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 dun. Okay, so right here. By the way, if I were to check what I just did, I just want to show you this real quick. This might help you. If you go to stat and then just go over to tests, remember we can be one of two tests. So one proportion z-test, or you can go to t-test right here. I'm sorry, it's right here, t-test. So one proportion z-test or t-test. So if I go to t-test here, I could literally plug in the stats. So this would be 7. This was 6.8. S of X was 0.5. Sample size was 40. And this was less than, right? Okay. Again, this will allow me to draw it. And this, just as a heads up, this will give me, by the way, that line right there, that was from my other class. So don't worry about that, either of those two lines. Just look at the middle part that's here. So if you look right here, that is our p-value right here. And our p-value was 0.0078. A little bit off from what I had, but pretty good. And then there's our test statistic right there, again, that I have to plug in. So if you mess up, again, you still have to show all the work, but that was pretty easy just knowing how to plug it in. Again, that's going to stat, t-test, and then going to one proportion z-test. Those are the two that you're going to be needing to be familiar with for at least this test. To go to the, let's say you don't know the standard deviation, you can always go to stat edit. Let's say the data was an L1. I'm just using previous data. You could then just go to stat, calc, 1var stats, make sure it's L1, no frequency, because there's no change in frequency. Everything takes on a value of 1. And so when I calculate that, that gives me my mean and then also my S of X, which is my standard deviation for my sample. Okay. Great question there. I hope that was helpful for you. Ryan, that was a good one there. Let me go to number 2. I'm not going to miss the, what part was I not going to miss? The concept list. That's what I wanted to make sure I hit that concept list hard. But let's go over one of these 4 steps. I'm going to hit this one a lot faster, mainly because we did one of these in class, but let's go ahead and go through it together. Again, by the way, you could always go to, if I was to kind of plug this into my calculator, I can always go to like a 1 proportion z-test and also check this as well. Okay. So let's go to our state part. First off, when I do this, it says this: the germination rates of seeds is defined as the proportion, heads up, proportion world, when properly planted and watered, sprout and grow. A certain variety of grass seed usually has a germination rate of 0.80. Probably going to be my null here. We'll keep reading though. And a company wants to see if spraying the seeds with a chemical that is known to change germination rates will change the germination rates of this grass species. They spray 400 seeds with a chemical, sample size. 307 of them germinate. So here we are. P hat is 307 over 400. I've got my null. I've got my alternative. Let's see what we've got here. Because we're P world, it'll be P is equal to, and we'll have to see where it's at, but we know it's 0.8 because that's the claim, right? So we're comparing this to the actual claim that's there, okay? And I'll do 307 divided by 400. This would be 0.768, okay? 68, okay, perfect. Up on top, it then says, does the results provide convincing evidence? By the way, when we go into other tests, convincing evidence always means that we're going to use some sort of test, right? So in this case, we're trying to use a sample to estimate to my population, where P would be the true proportion of seeds that germinate with the chemical, okay? With the chemical. And the question is does the chemical changes, convincing the chemical changes germination rates? Changes just simply means not equal to. It doesn't say less, it doesn't say greater. We're just going to say that it's not equal to 0.80, okay? Alpha level is not given, so we'll just say it's 0.05, and we'll continue off of that. Plan phase, we've already got the test up on here. Normally that would go down here. Number 1, we know it's an SRS. Number 2, N is less than or equal to 1/10 of big N. And I think that's true, right? Because 400 less than or equal to 1/10 of all plants sprayed. Yeah, so I would say, yeah, we're good on that one. Part 3, remember there's only one thing you have to have shown, and that's the law of large counts. This has to be true, and if it's not, then we can't approximate this as normal. But usually, especially in an FRQ setting, you're going to be good. Remember with P, we always put in 0.8, not the P hat. That's important. So we do this times 400, 0.2 times 400. This would be 320 is greater than or equal to 10, and 80 is greater than or equal to 10. So we're good there. So all our conditions, 1, 2, and 3 are all met. Okay, I might write random sample out, but you get the idea. Do phase, let's draw a picture here. Always start off with a picture. The center will always be what we state. In this case, it's 0.80. They're innocent till proven guilty. So whatever's stated, we have to go with that in the center. And we see is 0.768. In this case, it's to the left. And we're trying to, because it's to the left side, we're going to highlight 0.768 and anything less than. But because we're using the p-value of not equal to, we've got to make sure we multiply it by 2 to double whatever the p-value would be. So now let's find mu of p hat is equal to p is equal to 0.8. We've already done that. Sigma of p hat is equal to the square root of p times 1 minus p all over n. So that'd be 0.8 times 0.2 divided by 400, and then all square rooted, okay? So we're going 0.8 times 0.2 divided by 400 there. And we square root it to get 0.02. All right, good stuff. Now it becomes the normal distribution part, the normal CDF. So we'll use normal CDF. Again, make sure we write it out, lower, upper, mean, standard deviation. Also, you could use the z-score formula just as a heads up. You could use x bar minus mu. Make sure you use the general formula, which is value minus mean divided by standard deviation. And then you could plug in the actual formula. Just make sure that if I use this, z-score is a standardized value. If you go from here to down here, the mean would be 0. The standard deviation would be 1 because it's standardized with a z-score. So just be careful of that. Down here, unlike the TCDF, the normal CDF, I do not have to change 0.768 to a z-score. So I simply say negative 9999 to 0.768 to mean, which is 0.80. And standard deviation is 0.02. And let's see what it would be for just one side of it. So second distribution, normal CDF, negative 9999, comma 0.768, comma 0.8, comma 0.02. And there we are. I got, in this one, I got 0.0548. Multiplied by 2, though, gives me a p-value. So my p-value, and I'll put it over here just for sake of room. Maybe I'll do this. Delete that. Perfect. Get all of this out. Good stuff. Okay. So my p-value, after I multiplied it by 2, is equal to 0.1096. Okay, so now this becomes a different conclusion, which I'm glad we did. Let's just rewrite this again to make sure we're all clear. When comparing, let's go right straight into it. Let's try that again. Just because we could be kind of wordy with this. I want to make sure I hit it. Since our p-value, in this case is 0.1096, is greater than our alpha level, which is 0.05, we do not have convincing evidence to reject the null and state, here we go, we're stating the alternative, state that the true proportion of seeds germinated. If I wanted to keep going, germinated with a chemical, making sure I'm really clear, is not equal to 0.80. Now, let me make sure I say this again. We don't have convincing evidence because it's greater than our alpha level, right? What that means is that doesn't necessarily mean that the null is true. Y'all almost got me right there. Y'all almost got me. That the null is true. What it does say is that we do not have convincing evidence to reject the null and accept the alternative. So here's the thing, and I think Jaden said it or Brianna said it today. It's frustrating a little bit because when we show this, we do not have convincing evidence to reject the null. But in statistics, a lot of times when we're only having so much information, we're saying from our sample, when we estimate it to the population, can we find convincing evidence to reject our null hypothesis, accepting the alternative? Or do we not have convincing evidence to reject the null? Therefore, we don't have convincing evidence to accept the alternative. Do you see how that kind of goes hand in hand? I hope that does. I hope that makes sense as we talk through that together. So, yeah, I hope that helps there. Good stuff. A lot of questions here. Power, yes. Gotcha. I'm just looking at questions. Yeah, good question, Ryan. SRS and Jaden, I'm going to come back to that question because it's on the concept list, okay? Ryan, when we say from a certain variety, we're going to assume that it is an SRS. If it's a multiple choice and it asks for what area does it fail, you probably will say it. In an FRQ, you're not going to stop it at the second step more than likely on this. And so, yeah, that's what I would say on that. Cool. That's what I would say there. All right. Charles, are you finessing, Charles? I saw you're late there. No worries, man. Glad you're here. Yeah, Ryan, it's a little weird. I kind of fabricated that question a little bit. It'll be more clear on the FRQ what it's looking for on that. Cool. Cool. Oh, man. Yeah, Eric, I see a lot of questions on that. We can hit as many as we can. Eric, I appreciate you for being honest with me. Let me go over the concept list, and then I'll do that quickly, okay? Yeah, on 24, throw out 24. 24, you don't have to worry about a paired t-test. You're not old enough yet. I'm not concerned with that right now, okay? Power will always be given to us. We just need to know how to interpret it, okay? Good. All right, good stuff. There's a lot of questions here, so I'm going to hop right into it. First off, before I get to the multiple choice questions, could I please go over some of the just concept list real quick, okay? Number one, test statistic related to the p-value. That's what we've been doing, right? So when we look at, I'm sorry, this is a little different. My apology. So if I give you like the t is equal to 2.31, and I say, and I maybe give you some more information than that. I'm trying to think of what I could give you with the sample size of 30, and I say, what is the p-value right here, right? What we would do here, just as a heads up, is, well, we could just use TCDF. Does that make sense? So we would just go, we have our center, which doesn't necessarily matter. 2.31 is the standard deviations to the right of my mean. And if I'm finding my p-value, and let's say that we're talking about something where the alternative is mu is greater than whatever it is, fill in the blank. In this instance, we highlight this, and this is where we can go to TCDF lower 2.31, comma upper 9999, comma degrees of freedom, which would be 29 because it's 30 minus 1. And just knowing what I would do here. For a z-score, just make sure that when we use a z-score, let's say I was going to the proportion world, which would be what we would use z-score for. In this example, I would say that, let's say our z is negative 2.31. Again, here's 0. We're negative 2.31 standard deviations from the mean. That doesn't necessarily mean that that's the actual value. That looks like a T. Sorry, it's a Z. That just means that it's negative 2.31 standard deviations to the left of my mean. So let's say I was finding this p-value. When I put into normal CDF, because that, again, is the proportion world, and with the normal distribution with a z-score, it would be negative 9999, comma 2.31, comma 0, comma 1. And the reason why I use 0 and 1 is because when I use a standardized value has a mean of 1 and a standard deviation, mean of 0 and a standard deviation of 1, okay? It could be that negative 2.31 has a proportion of 0.8 and 0 has a proportion of 1.2. Or I'm sorry. No, that wouldn't make sense. My fault. I'm trying to back up. Maybe this would be a proportion of 0.75. And maybe down below, this might be something that's 0.6. But we change these values to z-scores. And what they want you to do is be able to know, if I give you a z-score, how do I change that to where I find the p-value? Okay. Yeah, know the graph, be able to explain how the test statistic relates to the p-value, similar to what I'm just saying right here. Remember and know the null and the alternative. So if we're talking mean world, and like the last one with the bulbs was mu equals 7 and mu is less than 7, know what to highlight. If it's not equal, remember it's both sides, and we have to multiply by 2 to get the full p-value there. Number 3, finding hypothesis from a scenario. It's pretty, we've been doing that quite a bit. No 4-step process for P and mu world. Again, we've done that already, hitting that pretty hard throughout this process. Cool. A lot of these relate. Number 5, know the conditions needing to be shown for each world. Very important, okay? State plane do conclude, but then also specifically remember with a t-distribution, know the 3 conditions for that compared to a normal distribution. And again, that's just another way of saying this is p world, this is mu or mean world. Type 1 and type 2 world and consequences. I may not have enough time to hit this, so if you need some help on this, come by for more help. tomorrow morning or Thursday morning. Be more than willing to help you on this. So I'm not going to hit this tonight, but I did hit this on a podcast. Number one's a really good one. Relates really nicely with those type 1 and type 2 parts there. So know the definition, know the consequences that relate to that. Also look at your last test on 6 as well. How does the significance level impact type 1 and type 2 error? Something that you need to know is that the probability of type 1 error is my alpha level, right? So let's say it's 0.05. The probability of type 2 is equal to 1 minus power, okay? Power is given to us, okay? So let's say power was 0.8 in this. That would mean that the probability of a type 2 error is 0.2, whereas the probability of a type 1 would be 0.05 in this scenario. Now, what if I decrease the alpha level to 0.01 instead of 0.05? Okay, so you got to think about this. That means my probability of type 1 error would decrease. Does that make sense? Because I changed the alpha level. However, we remember that in probability of type 2 error, what happens with power when I decrease the alpha level? When I decrease the alpha level, it's harder to be statistically significant, right? Because it's less than. So it decreases my power. Because of that, if this decreases, 1 minus a lower number would actually give me a higher probability of a type 2 error. So you have to look into it. I mean, it kind of applies it. But what that means is as the probability of type 1 error goes up, probability of type 2 error goes down. They kind of work opposites of each other. If I have in a situation where if the probability of type 1 error goes down, like the 0.01, right, because we changed the alpha level, what happens, though, is the probability of type 2 error will end up eventually going up if we changed what the alpha level would be there, okay? So just kind of know how those kind of coincide. Know the formulas, but then just know as one increases, the other will decrease. So it's kind of a little bit of a game of you're never going to have a perfect world in this. Just know that as I maybe decrease type 1, I might have to increase type 2 and vice versa, or it will increase type 2 and vice versa. Number 8, know number 7, how to explain a real world sense. Yeah, very similar to what I just said. So let's say that in a situation, the type 1 error is more serious, okay? Let's say we're talking about a lawsuit, and I think the lawsuit was the last test. If I go into the lawsuit and in the type 1 error, we reject the null, but the null is true. So I reject it, but it's actually true. And let's say that case, the type 1 error was the more serious of the two options based on my circumstance. I would want to have a lower type 1 error compared to type 2. So if I have the choice between a 0.01 alpha level and a 0.05 alpha level, in this example, because type 1 is more serious, I want to decrease type 1 error, even though it will increase type 2. So that's why I would use 0.01 compared to 0.05. On the contrary, if type 2 is more serious based on my consequence and based on my real world application, I would want to make sure that I would go with the higher alpha level, because as I do, this type 1 error would increase, but my type 2 would decrease, because again, they work opposites of each other, okay? Again, if you need a little more help on that, we can hit that in class or in the morning help session if you need a little bit of help on that. Cool? Providing convincing evidence. That's really important, okay? Interpreting a p-value. P-value is a little different. So basically, we know the conclusion, right? If I compare the p-value to the alpha level and the p-value is less than the alpha level, it's convincing, statistically significant, reject the null, right? But if it's greater than, we would say that we do not have convincing evidence. But a p-value, just as a heads up, is this definition. It's basically if we assuming the null is true it's the probability the event, whatever the event is, the event will occur purely by chance. Purely by chance. Okay. So if you remember the light bulb, in that light bulb illustration, we got a p-value of 0.006. So what the probability that my sample, I think was 6.8, would have, out of those 40 light bulbs, have an average of 6.8. That average, the probability that would happen purely by chance is 0.006, which is very low. And that's why we have convincing evidence. So just know the p-value is, we assume the null is true, and it's the probability the event will occur purely by chance. Okay. Defining power. All right. Power is just the probability. Probability that we, sorry, let me try this up here. That we will, let me go back here. I want to show you this because I know this is like the beautiful answer. So it's assuming the true mean is whatever it would be, right? Or true proportion would be whatever. There's a blank probability of finding convincing evidence against the null, right? So it's basically the probability that I will find convincing evidence against my null hypothesis. Cool? So that's really what it is. This is like the beautiful answer right here. But basically, it's just literally the probability that I'll find convincing evidence against my null hypothesis. Okay? So p-value is the probability it occurs purely by chance. The power is the probability that we'll find convincing evidence against the null. Cool? Hope that kind of helped there. Let's see. I think I'm going back. All right. Sorry to make you sick. All right. Next thing. Okay. Don't have to find that T procedure for mean world. No conditions. Yeah, I know that. Right. 3 conditions. Know the normal here. Make sure that you know all 3 and we go in order. Right. And only one needs to be met. Just a heads up there. Type 1, type 2. Defining it in context. Make sure of that. We just said that. Finding null and alternative. Using p-value, comparing it to the alpha level. Confidence intervals and hypothesis. If the null hypothesis is inside the interval, yeah, this is a good one. I'm going to look at one of these here in a second. We went through robust, finding hypothesis, type 2 error interpretation, and not equals. Remember, that means I'm shading both sides. Cool. All right, so let me go to this one because this one's a really good one, and I think it's one that Eric was hitting on. It's number 8. So this right here is 95% confidence interval. The null hypothesis says that p is equal to 0.3. Therefore, if 0.3 is not inside of one of my confidence intervals, meaning if it's not in one of these, it means that it is outside of the 95%, meaning that it is, let me give you a visual here. If it's not in my 95% confidence interval, think about this. That means it's outside of this and is in my 5%. So yes, we didn't necessarily hit this part. We did in chapter 8. But what that means is if it's outside, if my null, the 0.3, is outside of my confidence interval, then it is statistically significant to say that, especially when we're talking about not equals, we have evidence to say that we reject the null and then accept the alternative. So we're not using a p-value. We're just comparing the null to each of the confidence intervals. So 0.3 is inside of A. It's also inside C. It's also in D on the outside. When I look at part B, though, notice 0.3 is on the outside. It's like over here in this tail. And it's outside of the 95%, and it's actually in my 5%. Therefore, that would be the one area that we would have evidence to reject the null hypothesis. Okay, so when it falls outside of that confidence interval, that's there. Cool. All right, I see a couple other questions. Let me just hit those real quick. I think, Eric, it's a great question. I think it's on there, dude. In fact, here, I'll give this to you just in case. I thought I have them on there. If they're not on there, my B ad. Here they are, y'all. Woo! Hopefully they come to you. You can see them. Hey, let me just say this. For the answers, I want everyone just as a celebratory, exciting thing. Just give me a all right. Give me a little bit of a trumpet. Very good. Okay. Nicely done. All right, let's pull this up here. Let's keep going because I know we've got questions. Oh, hold up. Chapter 9. Very appreciate comrades. Oh, you got it, Eric. I'm sorry. Okay, so yeah, okay, Eric, great question. When we look at the question that you just had about Z-score, yes, you're correct. T-score, we plug in for TCDF. On a multiple choice question, if all I gave you was a Z-score and you had to use Z-score, again, you don't have to. As long as you show the formulas on the FRQ, you're fine. But on a multiple choice, if all I give you is Z-score, just know that I would be going into normal CDF with that Z-score. And in that instance, I would have a mean of 0 and a standard deviation of 1. Don't think of that as a FRQ. Think of that as a multiple choice. That's all they gave me type of thing. Does that make sense? So yeah, you're technically right there. Okay. When finding p-value with z-score is always 1 and the mean is always 0. Yes, Lindsay, you're right. Okay. You are right. Hey, I'm hoping that this is helping y'all. We are going to do a little bonus time. If you're done for the night, man, I completely understand. I know that we're going through quite a few problems here. We're being very thorough, which I appreciate. Let's go ahead through the questions here that Eric posed. And if I didn't hit your question, I apologize. Well, let's go through these together and then we'll rock and roll. Part 6, was a missed problem today. I was surprised, mainly because when we're looking at this, we've got to notice that it's an unknown population proportion. So we're in the P world. So what is not a condition? Well, the one that wouldn't be a condition would be where the population distribution should be approximately normal. The reason why C is the answer is because this would refer to mean world, and what they asked for was proportion world on number 6. So a lot of people put B, but that's the 10% condition. D is obviously right. E is right. That's there. And really B, if B is not a condition, then we would use E, but the answer that would be the one that we're looking for is C, because that's mean world there. Okay. Number 12, and Eric, stop me if you have a question here. After checking the conditions that are met, you perform a sig test of 1, mu equals 1, and mu is not equal to 1. You obtain a p-value of 0.022. Which of the following is true? Now, this relates to a confidence interval. Okay. So here's our 95%. Because our p-value is statistically significant, this means that our value is either on the lower or upper side of our 95%, because it's got to fall in my 5% to be statistically significant. Therefore, mu equals 1 would fall outside of this 95% confidence interval. So I want to make sure. Significance test. And the p-value would be 0.022, meaning that it would not be statistically significant at a 0.01 level, right? So that means that a 99% confidence interval would actually include a 1. You follow me? Because if it's not statistically significant at a 0.01 alpha level, then we would say that in this instance, that 99% would not, that 99% confidence interval would contain mu equals 1. So when we look at the 95%, though, we know that it will include the value of 1 because it always refers to not 0, but the value related to my null hypothesis. Okay, so that would be A. Cool. That was kind of related to the last one a little bit, maybe a little tougher. 13. Moving. Yeah, so this one says, which of the following conditions for performing a paired t-test is not met? Okay, so let's go through the random condition. An effect on people's behavior. Researchers collect data on the numbers of shoppers at a sample of 45 different grocery stores on Friday the 6th and Friday the 13th in the same month. Each store on these 2 days. Well, that's not really random, y'all. I don't think that's random. Sample of 45 different grocery stores on the same day. Yeah, I would say that this is not met. Random is not met. Let's go to the normal condition. It never says the population is normal. So we look at, is n greater than or equal to 30? And I think it is because, hold up, how many? We go to 45 different grocery stores. And each grocery store is a different sample size. So 45 is greater than or equal to 30. So we would go there. And this is a paired t-test, by the way, which is a little different. We'll talk about that later. But what you do need to know is that the conditions are the same. Okay. So we would say that this is, in fact, normal. And independent would be 1/10, a big N. And that I think that would be good, right? So 45 is less than or equal to 1/10 of all stores. Yeah, I would say that that's good. So the only one that fails is A, and that's why A would be the correct wrong answer, or the one that didn't get met. Okay, cool. 14. I think that we're going to the next one here. 14. The most important condition for sound conclusions from statistical inference is that. Oh, this is a good one. I'm not going to look at the answer for this one. I want to see. Sound conclusions. Okay, remember the robust example? The most important thing, not that the population distribution is normal, not that the data contain no outliers, not even that the sample size be more than, and not even E. The most important thing is that it comes from A, a random sample, right? And the reason why that is because that allows things to be robust, which if I do take a well-designed random sample, that allows me to overcome some inefficiencies with some of these other things possibly, okay? So that's why A is the most important based on the robust factor that's there. All right, 16 and 17, we are rolling tonight. This might be the best podcast, y'all. We need shirts. We need some shirts. We need to get some shirts made, all right? We're going to do that. We're going to make them. 16. We're thinking of conducting a one-sample t-test about a population using a 0.05 sig level. Suspect that the distribution is not normal and may be moderately skewed. Which of the following statements is correct? You should not carry out the test because the population does not have a normal distribution. We'll hold off on that. B, you can safely carry out the test if your sample size is large and there are no outliers. Well, if the sample size is large, the no outliers thing doesn't really matter. So I would say B is incorrect. C, you can safely carry out the test if there are no outliers regardless of the sample size. Or skewness, right? Really, C is incorrect because if it's skewed, if it's moderately skewed, you could kind of go one way or another with that. Yeah, let me backtrack here. Actually, let me backtrack. D is incorrect. I want to go back here. T-procedures are robust. You can use them anytime you want. No, that's not true. Even though they are robust, especially if it's a good SRS, that doesn't mean you can use them whenever you want. Okay, A is incorrect. I'm right here between B and C. B, I threw out initially. You could safely carry out the test if your sample size is large and there are no outliers. I don't like this question, and here's why. Mainly because there's three conditions, right? Condition one, population distribution, is it normal, right? Is it normal? That's condition one. Condition two is n greater than or equal to 30. Condition three, sample size of 1/10 of big N, right? Oh, I'm sorry. Good night. I was thinking of something different. This is the skewness, right? So major skew and no major outliers. Okay. I don't like B. I mean, I don't like C because you can safely carry out the test if there are no outliers regardless of the sample size. That's not true because it's moderately skewed, possibly. B is the best worst answer. I don't like it because it says you could safely carry out the test if your sample size is large. If it's large, assuming it's greater than or equal to 30, it doesn't matter whether there are outliers or not because condition two, by basis of the central limit theorem, would be met. So I don't like 16. Just make sure you know these three and apply it in that way. B is the best worst answer. I know that may not be great for you, but that's kind of the reality there. All right, 17. The hypothesis are null, suspect is innocent versus suspect is guilty. Then we could estimate the probability that experts who interpret lie detector tests will make a type 2 error, which is we fail to reject null, but HA is true. Okay, so our decision would be is that we failed to reject the null. Suspect is innocent, right? So we failed to reject this, but the alternative is true. So let's go through this. So this is true, right? This is true here. Remember, type 2 error is 1 minus power is the probability that's here. But in looking at this, you could kind of deduce that, okay, suspect is guilty is the alternative. So what is the probability that we would fail to reject the null, but the alternative is true? The alternative is true is kind of what's been given. We failed to reject the null would be that we find them as having as being guilty. Okay, so that would mean that we would say this could possibly be 15 right here, because if we fail to reject, right, we failed to reject, meaning that the suspect is guilty, we failed to do that, that would be, we would say that he's innocent, that'd be 15 over the total of 140. So the probability would be 15 over my total possibilities, which is 140, which is C. Okay. So we failed to reject the null, but the alternative is true. Again, this is the true status. The alternative is true. The fact that they're guilty. However, I said that they were innocent. That is type 2 error, and therefore it would be 15 out of my total of 140. Okay. Last one, and I'll go to some last minute questions. 95% confidence interval is calculated to be, assume the conditions for performing inference are met. What can we draw for a test where mu is equal to 2? Again, that is in between my confidence interval. So just based on this alone, because it's inside, we do not have convincing evidence, right? Have convincing evidence. And because it's not equal to, and it's at a 95, at a 0.05 alpha level, okay? Sorry, level. Okay. What conclusion can we draw? We would reject the null. Okay, that's not true because it's inside. We'd fail to reject the null. Yeah, that would be probably true. C is none. Confidence intervals and significance tests are unrelated procedures. That's not true because we're talking about significance in the confidence interval, right? Right. No, that's not true. Yeah, that's not true either. And that's how we would attack this here within this one. And yeah, cool beans. Let's see if we can go to last minute questions. 16. Phew, 12 is C. Oh, yeah. So, Eric, on that last question, and I'll go up to your previous one, the 15 over 140 is not the power. You follow me? You never have to find power. Power is given to you, and you subtract 1, or you subtract power minus 1 from 1, and then that would be type 2 error. What we're saying is in a real-world setting, based upon that chart that they gave us, the probability of it being a type 2 error would be 15 over 140. Okay, where we failed to reject, or failed to reject the null, but the alternative is true. Okay, and that would be not the formula 1 minus power. That's different. That would be just simply 15 over 140. Great question though. Number 12 is C. Is 12 C? Let's see here. See, number 12 is incorrect, y'all. That is incorrect. The correct answer would be oh, I backtracked. No, you're right. You're right. I did this backwards. I'm sorry, y'all. I missed this one. Dadgummit, because we were trying to teach this too. Think of this as it is statistically significant here. Because it's statistically significant, that means 1 falls outside of my 95% confidence interval from here to here, right? So 1 would fall outside of my confidence interval of 95%. So I was looking at this. I didn't read it right. A 95% confidence interval will include the 1. That's actually incorrect, mainly because when we look at it, the 1 would actually be outside of it because it is statistically significant. When it's not statistically significant, what we say is that the 99%, the p-value is not statistically significant here. Therefore, the 1 should be inside of the confidence interval, and therefore C is my correct answer. Okay. That was my fault. I literally, I just messed up on that. My apologies, y'all. All righty. Oh man, that was a late study session. Did we almost go till, man, that was almost an hour 15, y'all. Yeah, Claudia, I'll do it quick, okay? So robust means that in the situation of a t distribution, there are times where we're not going to have the perfect data that's there. For instance, a lot of times a population that we're trying to assess, we either don't know it's approximately normal or it's not approximately normal. It's skewed one way or another, right? So in that situation, we want something in a t distribution. A t distribution is robust, which means that major outliers or major skewness does not impact the results of the data, as long as a simple random sample is taken and represents our population. So that's what robust means. Does that make sense? So it's unaffected by major outliers or skewness. Cool. That's what the robust means. That's a good question. Cool. Looking at anything else. Eric, I feel as though I had a couple of things that maybe I messed up on in terms of, or maybe I could have gone through more in depth. I know the confidence interval, I want to make sure I go over with you again. So if you want to come in tomorrow morning, feel free and we can go over some of those other ones that are there. It seems as though that many of your questions are very much the same. So I wouldn't worry too much about it. I think it's one concept with those confidence intervals. And from what I remember, there were one of those questions on the test. And so we'll look at one of those maybe tomorrow morning, and I'll give you a Q&A on that and then go from there, okay? Hey, I'll be there by 7:30 tomorrow. Pre-Cal 12 should not be there. They don't really have a whole lot going on, maybe one or two that need some help with the homework. But overall, that was should be good. So come in tomorrow morning, come in on Thursday morning, get some help there, and we'll be rocking. Y'all, thank you so much, and y'all rock. I really appreciate it. Y'all are awesome. Y'all are finessing all day long. Y'all finesse, and I appreciate that. Charles, there, that was for you. That was for you. Have a great day, y'all. Have a good one. Stay classy. See y'all.